Okay, so let's continue with our study of how ideals split in number fields. And next up is probably one of the most useful theorems for doing explicit calculations. But the proof is also a bit technical, so it'll be a bit of a long proof and quite a lot of generality. But afterwards, I'll tell you exactly how we're going to use this to explicitly take a prime number, look at the ideal it generates in some number field, and then explicitly figure out what prime ideals, divide it. So write as a product of prime ideals, and so on. So this is theorem 3.5.10, and it's called Dedekind-Kummer theorem. And it says the following: I'm going to let K over F be an extension of number fields. Later on, I'll give you as a corollary the case where F is just Q. In that case, like, the notation will simplify a lot, and that'll probably be the case that we study the most. But the proof is no harder in this level of generality, so I might as well prove it as general as possible. So I have an extension of number fields, and I take some alpha in OK, a primitive element. I.e. such that K is isomorphic to Q adjoin alpha. I'm going to let goth P be a prime ideal in OF, so in my bottom field, and P, the normal P, just be the prime number such that, and if you take this ideal and intersect it with Z, you just get. So we know this, that above, below every ideal of OF lies a ideal of Z, for example. So in this case, if this is prime ideal at the top, you're going to end up with prime ideal at the bottom. We've seen this. So it's going to be generated by some prime number. I'm going to take P to be this prime number. That'll be a unique prime number that's in there. And I'm going to make an important assumption. So this theorem will only work under the following assumption. And I'm going to assume that P does not divide the index, this following index of OK to OF adjoin alpha. So what does this mean? I'm thinking of this as a group, as a subgroup of OK. This is just the, take the ring generated by OF and alpha and then just forget that it's a ring and just think of it as an additive group. And I just mean the size of this quotient by this quotient as groups. So I'm going to assume that P doesn't divide this index. So P won't have to divide this number. So what's this theorem going to say? So I'm going to let, I already have this notation. I'm going to let M alpha of F be the minimal polynomial of alpha over F. And I'm going to let M alpha F bar denote its reduction mod P, but not mod P the prime ideal, but P the prime ideal. So I'm going to let this be the element of OF mod PX. So P is a prime ideal of OF. I can quotient out OF by P. I get some sort of, I'm going to get a field, and this, because all these prime ideals are maximal, this is a field, and this is just a polynomial ring with coefficients in this field. And so this is, think of this as the reduction mod this ideal of this polynomial. So this is a polynomial, and then I reduce mod goth P all the coefficients. So I'm going to take M alpha to be its reduction mod P, so it's mod frac P. So now the key of this theorem tells us that the factorization of this polynomial in this ring tells us about how this prime ideal factors in my field K. So if I write M alpha of F bar as m1 bar of x to the e1, m2 bar of x to the mr to the er, with the mi's bars distinct irreducible polys in OF mod in this ring, then I have this factor. I've taken my ideal and I've factorized in a bunch of other ideals. These are, in practice, these will be like ideals over FP for some prime. So over the finite field with P elements. So you're taking a polynomial, you'll factor into its irreducible components, and now I'm just going to pick a lift of them back to characteristics. So back up to my original ring. So I'm going to let this mi be a polynomial in OFX such that it reduces to mi bar mod P. Then still lots of. Then I'm going to let this such that it reduces to mod P, and I'm going to let PK. To give you the name, PIK be the following ideal: P mi of F, which if you go back to like sheet 1, you'll check that this is just the ideal generated by P. Okay. Plus this ideal. So we saw the ideal generated by two things is the same thing as the sum of the two ideals. Here I do P OK because I'm thinking of P, which was an ideal of OF. I'm thinking of it now as an ideal of OK. And this is going to define me an ideal in OK now in my dot field. So then what is the statement of the theorem? Well, there's three parts. One, the ideals P, I, K, first of all, are independent of choice of mi. So remember, I had my mi bars, which were the factorization coming from factorizing this polynomial uniquely into irreducible polynomials, and then I was just taking some lift of it to OFX. So this is a typo here. This should say OF mod P. Then I just took some polynomial who reduced onto the bottom. First thing is that this is independent of choice. This is actually immediate from its construction. If you look at how I've constructed it, if I had two different ones, if I had two different lifts, then their difference, because they're lifts from mod goth P, their difference would be an element of P, so this ideal wouldn't change. So these things are independent of choice. But I think I'll just state it there. Two, these PIK are distinct prime ideals. And they are precisely the prime ideals lying above P. So precisely the prime ideals over my Gothic P, i.e., if I look at this times OK, the ideal generates an OK. This is going to be PI1K to the E1 PRK to the ER. Where notice that these ERs are exactly the same ones showing up here. So this factorization is, from this factorization, I've constructed some prime ideals, or at least I'm claiming that these are prime ideals, and then that immediately tells me how my my ideal factorizes in OK. And thirdly, this residue degree of this to to P is the degree of these polynomials, these mi bars, and the ei's is the same thing as the ramification degree. So pik to B. Notation to fix. Okay, so before getting into proof, let me just go through this again. So we have an extension of number fields, k over f. And I have picked some primitive element so that my field looks like this. And I have a prime ideal in my bottom field. So a prime ideal in OF. And little p is just a prime number such that this, when you intersect this ideal with z, you're always going to get a prime. So if you go back to your notes, you'll find out that if you take a prime ideal and you intersect it with in some number field and you intersect it with z, you're going to get an ideal generated by a prime number. And this is what my prime number is, p. And my assumption is that this little prime number p doesn't divide this index. This is the ring of integers of OK. Quotient out, this is the size of this, well, let me just write this here. This is the size of this quotient. Thought of as groups. So my assumption is that p doesn't divide this thing. Then my claim is that if I look at the minimal polynomial of alpha over f, so this is the minimal polynomial of alpha over f, and I look at its reduction mod, the prime ideal that I'm interested in, this frac p, then if I factorize its reduction into prime ideals, so this factorization tells me how this ideal is going to factor in OK, so in the top field. And the recipe is, well, out of these, I'm going to construct these ideals, which is just the ideal generated by p and mi of alpha. So I take this polynomial, which is working mod p, and I lift it to some polynomial here. Doesn't matter how I lift it. Just find some polynomials which such that when you reduce mod p, the coefficients mod p, you get the original one. And then my claim is that this is a prime ideal, and it's precisely this p OK. So this ideal in my top field now factorizes the product of these prime ideals, and these exponents that show up are exactly the exponents showing up here, and the residue degrees are exactly the degrees of each of these components. Okay. If it's still a bit overwhelming with the notation, then don't worry. I'm going to give you a corollary with easier notation right at the end after this, and then it'll be easier to see what's going on. So the proof, I'm going to make 3 claims. I'm going to prove 3 different claims, and I assume I'm going to show you that the theorem follows from these claims. So the result follows from the following 3 claims. So what are they? So A, I claim that if I let fi be the degree of mi bar, then for each I, either this pik is the whole ring, or OK mod pik is a field of size of mod p to the fi. So I have this claim. The next one is that these ideals are coprime. The I and j, this is, well, 1 generated by 1, which is okay. Whenever, if I is different from j, so whenever the I is different to j, these ideals are coprime. And the third claim, C, is that this ideal, the ideal that P generates in OK, divides Pi1k to the E1 times Pi rk to the ER. Okay, so let me show you that if once I've proven these 3 claims that I get the result. From A, B, and C, the result, the theorem follows. Let me prove this. So by relabeling these PIKs, we can assume that if I relabel, so the first ones are the non-trivial ones. So if I go PSK, so all of these are not the full ring, and the other ones all of the other ones are full. So I'm going to start by just doing this. I'm assuming that for each of these, either they look like the full ring or something about the size of the residue field. So let me just say S is the ones which aren't. The first S are the ones which aren't the full ring, and the remaining ones are the full ring. Then by B, well, sorry, not by B, by A. By A, these are prime ideals. Since I've quotiented them out, I've taken a look at the quotient and I've gotten a field of size this. So if I take a ring and I quotient out, I get I get a maximum ideal. If I quotient out a ring by an ideal and I get a field, then I get a maximum ideal. In particular, it's prime. So these are prime ideals. Moreover, by construction, they all contain my original ideal P. Remember that these PIKs were defined to be the ideal generated by P and some other thing. So clearly they contain this ideal P. So by construction they all contain this ideal P, and so they lie above it. So lie above. Now that's how we said it. So they lie above P, and the residue degree is exactly Fi. Just look at the definition of how residue degrees are defined. The residue degree would be the index of this field over this field OF mod P. And once you know that this is a field the size of Fi, then this is explicitly telling you that the residue degrees map like this. So let me go back and look at the definition of residue degree to see why this is the case. So this part A tells me that these will be prime ideals and they contain P, and it tells me something about the residue degrees. Part B tells me that says that these BIKs are well, let me make sure clear up on the first ones. These first S ones, which are non-trivial, are all distinct. And part C becomes the following. It says, well, I said that POK divides this. So I'm just going to write this in notation. POK divides P 1K to the E1, PSK to the ES. Notice that here I was going all the way up to R, but I'm assuming that after S they're all trivial, so that they're the full ring, so it won't change anything. So it becomes this. So if I have this sort of divisibility, what does this tell me about the ideal that I have? So I'm telling you that POK divides this product of prime ideals. So somehow, just as in this would work for normal integers, this means that that if I look at what this ideal is, this is going to be I1K to the D1, B, SK to the DS, with these DIs less than or equal to the EIs. Now, I'm not sure if I gave this a name in the notes, but last lecture, this was given a number 3.4 in the notes. I proved this sort of relationship between the residue degrees the ramification degree is the rigidity degree and the degree of the field. And I'm going to use this now. So using this equation 3.4, we have that the degree of this field is the sum I equals 1 to s of the di's times the fi's, because I factored my prime, and that result 3.4 told me that the degree of k over f is the same as the sum of over these di's times the fi's, where fi's are the rigidity degrees. So we have this sort of thing. But on the other hand, we know that the degree of the minimal polynomial, this degree is the same as the degree of the extension, which if you look at how I constructed these EIs, this is going to be the sum of these EIs and the FIs, because I've taken my, where was this? I took my polynomial and reduced it mod p, or mod my ideal p, and got this. Notice that the degree is going to be preserved by this, because this is a polynomial of some algebraic integer, so the initial coefficient is 1. So the degree always stays the same. So if this was a polynomial of degree 10, then its reduction is going to stay a polynomial of degree 10, because the coefficient of x to the 10 is 1. So it survives reduction mod any prime ideal. So I have these two things. So if you put them together, this implies, so this means R has to equal S, and the DIs have to equal the EIs, which gives a proof, which gives a theorem. Okay, so I just need to prove these three claims. So I have these three claims to prove, and I just showed you how the theorem follows from this. So then let's go to this claim. This is going to be the hardest. The first one's the hardest one to prove. So nope, don't want that. Proof of the following. So this is to remind you what the claim was. Of this claim. Okay, so this just follows from messing around with ring theory and maps between the rings. So note that each mi bar, so each reduction of my thing, each factor showing up in the reduction of my minimal polynomial, by construction is irreducible. Irreducible poly in OF mod P X. So I'm going to just ease notation. So if I'm going to let E denote this field. Denote the field. Denote this field. And I let, say, mi denote the quotient of this field by this polynomial. So I have a polynomial ring quotient out by an irreducible polynomial. So again, this is a field. Then this mi is again a field. So notice this, and notice that we have a map from OF X to this field. What's it given by? Well, you first reduce mod P, and then you reduce mod mi. So we got a map like this, given by first reducing mod P, and then mod this mi bar. if you think about this is almost by construction, this map is surjective. And if you think what's the kernel, and its kernel is an ideal. So it's going to be an ideal in OF X in this polynomial ring, generated by P, and this lift of this polynomial Mi. So I've done to get this map. I've done two reductions. Sorry, to get this map, I've done two reductions. I've reduced mod P and I've reduced mod Mi bar. Remember, Mi bar was just I took my middle polynomial, reduced mod P, and then factored it. And I defined Mi to be any polynomial in this thing which reduced to the same thing. So if you have a think, then you'll see that the kernel is just going to be the composition of the kernels of the two maps that I have. In this case, this Mi bar turns into Mi because I need to take it, because I'm in OFX. I need to take a polynomial in OFX, not in EX. So the map is surjective and the kernel is generated by these two things. So what does this mean? So we have an isomorphism. I have a surjective map and I figured out what the kernel is, so I have an isomorphism from here to this Mi. And well, this map is given by what? You send X and you evaluate at alpha. So you do this and then reduce mod P. Mod ideal P. Now, by definition, it's clear that, well, if you just look at how I defined it, these PIKs, which were this this thing, and then this polynomial. So let me just put NX here. This is the polynomial in X. If you look up this was my definition of this ideal BIK. Then it's clear that this polynomial is in this is going to be in this kernel. It's going to be in this thing here. So since this idea, because this Mi is a field, since this is a maximal ideal. Oh, well, so by definition, it's clear that I forgot to. I missed a section. Sorry. By definition, it's clear that this ideal I see where I messed up. 1 second. This is what I've skipped a line in my proof. So I have this map from OFX mod this ideal to Mi, but also note that we have a map phi from OFX to OK mod BIK given by this is a map given by I already got this messed up. It's given by this. Let me just move everything across and fix this. Yeah, sorry. So yeah, this I got my things messed up. So my original isomorphism here was between this ring, this quotient ring, and this Mi, which is some polynomial ring mod Mi. And now I have a similar map another map from OF, but now to OK mod PIK, and it's given by evaluating, because here there's no x's. So I first evaluate x and alpha, and then I reduce mod p. So the map given by sending x to alpha, and reducing mod p. So it's the kernel of this that I want to study. I want to study the kernel of this. If you look at the definition of this BIK, so this is this element here, this element that I'm pushing out by. By definition of this ideal, it's clear that this x is in the kernel of this theta map. Right? If you look at this ideal and you map it, look at the image under this, I'm going to send x to mi of alpha, and then I'm going to reduce mod p, and then remember that this ideal was exactly mi of alpha mod p. So once I evaluate this at alpha, I essentially get this polynomial here. So it's clear by that since since this is this, we have this in the kernel. But since this is maximal, so since this ideal I had above is maximal, because note that this is a field, so I've quotiented out our ring by an ideal and a kind of field, so this ideal has to be maximal. So since this is maximal, we must have that the kernel of phi is either this ideal, or it's the whole ring. So I have a map between, I have this map here. I've figured out what I possibility for what the kernel should be, and I'm not going to tell you this map is surjective. So next, we claim this map is surjective. When I say this map, I claim that. I'll give this an name. Phi surjective. To see this, we prove that. Just do this as groups, I guess. That OK is the same thing as the group generated by OF and alpha and elements in PIOK. So it's just the group generated by these two things. Clearly, this side is a subgroup of this. This is just a subgroup of OK. So this side is the subgroup of OK generated by elements in here. Sums of elements in these two things. Turns out that something stronger is true. Turns out that OF alpha plus P times OK equals OK. This is stronger. Which is stronger as P. Okay, this is P now, my little prime number P. As this is contained in PIK, so this is an actual stronger result. So to prove this is where we're finally going to use our assumption in the theorem. So let's go all the way back to the theorem. There's one assumption that we had, which was that the prime number P does not divide this index. So let me show you how we use this. By the way, this part A is the hardest one to prove. Part B and C are going to be pretty quick after we have this. We're almost done with this, but this is the longest bit. So to prove this, we make use of our assumption that P does not divide the index of OF alpha in OK. How do we use this? So here's the thing to note. So I note, but this is maybe you have to think about why it's the case. But note that the index of this subgroup OF alpha plus BIK, oh, not BIK, POK. No, the index of this thing must divide both the following index. It has to divide this index and this index. So somehow this is essentially the Tower law for group quotients in some sense. I have the group generated by these two things, and I have here's a subgroup and here's another subgroup. And I'm saying that the full index from OK to this thing somehow is a product of, well, if you do use a Tower law, then at one point you're going to get this factor, and at another point if you rewrite it in a different way, you're going to get this factor showing up. So this is maybe, okay, I'm going to tell you that this is just the Tower law for like group quotients in disguise, telling you why the index of this in OK has to be divisible by both of these two things. But OK mod POK is some power of P. Remember, this is literally maybe I'll, by definition, the norm of POK, which is this. This is just the norm of the ideal. This is like the norm. Well, go back. This is the ideal generated by the prime number P in OK. If you remember, we know how to figure out what the size of the norm of this ideal is. It's just the norm of the prime number P to the degree of the field, which is gonna, if you work it out, it's going to be some power of P. So it says some power of P. And by assumption, P doesn't divide this index. So these indices are coprime. And therefore, what do we have? We have that this index, the one that we care about, equals 1, which implies that OK is which is what I need to prove. So therefore, the kernel of phi is either this BIK or the whole thing. So it follows that we have either OK mod BIK is isomorphic to MI, or this BIK is not isomorphic, is the full ring. So it follows that. So it follows that this or this respectively. Okay. So yeah, in the first case, if the kernel is this, then what I've told you is that this was the map phi. It was a map from OK to this. I've just said that either the kernel is this ideal MIX, in which case this is an isomorphism, and in which case, yeah, I know that this. I figured out what the I figured out what the kernel is, or that the kernel is the full thing, in which case my ideal is trivial. And remember, this is what I wanted to prove. My claim A was that each of these, that for each I, either this thing was a full ring, or this thing was a field of the right size, and we've seen this. So this was a EI, and EI is a field. Yeah, MI is a field, and what's the size of this field? Well, we've seen this before, but maybe not with finite rings, finite fields. That this is a finite field, and the size of this is going to be the size of E to the power of the degree of this thing. Okay, so this is part A done. Great. So, but I said, I promise part B and C are easier of this claim. Part B was that these ideals were co-prime if I and J were co-prime. Line. So proof of this bit. So by construction, the MI bars are irreducible polynomials in E of x. I'm using the same notation, E as above. Therefore, I should call it EIX, but I'm just no, it's the same E. It's not. There's no dependence on I. It's just OF mod P. Therefore, for I different from J, we can find two other polynomials, say F bar and G bar in EX, such that MI bar G bar plus MJ bar plus F bar equals 1 in this polynomial ring. This means that, so I'm just trying to check that these ideals are co-prime. So I'm just looking at these MIs, which are showing up in the definition of these BIs, and I'm going to show that I can get the number 1 in them. So what does this mean? This means that I can find, say, some G and F now in OFX, such that MI times G plus MJ times F is congruent to 1 mod from ideal P. This is the same. We're just rewriting the same statement, but now instead of using bars, I'm using the mod P. So if we simply evaluate this expression of, this is some expression of polynomials at x equals alpha, we see, what do you see again? Mi of alpha, G of alpha plus Mj of alpha, F of alpha, congruent to 1 mod mod P. Therefore, 1 is contained in this ideal generated by this, Mi of alpha, Mj of alpha, which go back to problem sheet 1, and you'll see that this is the sum of these two ideals. Great. So this is part B, and part C was that POK divides this this product of primes Great, so let's do this. So just go back to the definitions. Since this BI of K was by definition this ideal generated by this, it follows that just look at this product of ideals. Do more. So these BIK to B1 to E1 times BRK to the ER. This is contained in, if you just multiply out, write out what, put this in where, in each of the corresponding ones and multiply it out, you'll see that this ideal is contained in the following ideal. M1 of alpha to the E1, product MR of alpha to the ER. So the ideal generated by P and these two things. Again, so replace each of these ideals with its definition and multiply it out and just play around with the ideals, and you'll see that they have to be contained in this ideal generated by P and this. But this means, remember that containment turns into division for ideals. This means that, let's say by, what is it, corollary 3.3.14, that BI1K to the E1 is divisible by this ideal here that I've just, this containment turns into division by this corollary. But note that if I take this, what's this? What do I know about these MIs of alpha? I know that M1 bar of alpha to the E1 product MR bar of alpha to the ER. This is the same thing as the minimal polynomial, the reduction of the minimal polynomial to alpha, which is exactly 0. Therefore, so I know something about this product. Therefore, this product M1 alpha to the E1, so without the bars, this is congruent to 0 mod P OK. Thus, so this thing is contained in P OK, and this is P OK. So therefore, we have P M1 alpha to the E1 1 alpha to the ER equals this P OK. So I'm telling you that they're the same. So I'm telling you that, yeah, from this, I'm saying that this divides this. So I'm talking about something of containment, and I've just rewritten that as this idea which I get from looking at this product of things being okay. So which gives the result. Okay, finally, this is the end of the proof. That was a long theorem, lots of claims, and a lot of notation. So let me just show you what this means in practice. So here's the corollary. Before I finish, corollary 3.5.11. Here's how I look at this. So this is the simplest case. So I'm going to let K over Q be a number field. Of degree n over q, and say alpha in OK a primitive element. I'm going to let P be a prime number. Not dividing the following quotient, this by this. So a lot of the time, these two. So sometimes these two things will be the same thing, in which case this is number is 1, and so it'll work for any prime number. And other times this might not be the number 1. There might be some numbers in there like the number 2, so you wouldn't be able to work with the prime equals 2 for this thing. Anyway, pick any prime number so it's not dividing this index, and I'm going to look at the minimal polynomial of alpha, and I'm going to reduce it mod p. Here mod p is literally mod the prime p. So this is, I'm going to write this as m1 r to the e1, m1, mr of x to the er. It's reduction mod p with these mi bars irreducible and distinct. So I'm just taking my polynomial and factored it. Then in OK, so in my ring of integers, the ideal generated by p factors as, well, can be written as this, can be written as the following. So you can write the generated by p, maybe okay, in OK if you want to be precise. This is the product over I equals 1 to r of some ideals pi to the ei, where this pi is just, you take the prime number p and then you just take any lift of these polynomials. These are polynomials working in characteristic p, so mod p, and just take any polynomial which reduces to mi bar in z, the coefficients in z, and just evaluate them at alpha. So this is what this pi is, and the residue degree of this is going to be the degree of this mi bar, if you want, and ei is going to be these ei showing up here will be the ramification degrees. Great. Okay, so next time I'll do a bunch of examples of this to show you in practice how it's working. But this is not really the version of the thing that we're going to use the most. But the proof of this is no easier than the proof of the other one, so might as well prove it in general. Ooh. Okay, so I'll stop here.